Have you ever encountered a chemical reaction that just seems to, well, flow? No awkward detours, no unstable pit stops, just a single elegant step where bonds form and break in perfect synchronicity.
It's the kind of chemistry that feels almost intuitive once you grasp the underlying principles. Think of it as um, molecular choreography, really.
Welcome back to the deep dive. Today we're taking a deep dive into pericyclic reactions, specifically focusing on cycloadditions from Chapter 34 of Clayden, Greaves, and Warren's Organic Chemistry. We're talking about a whole new class of transformations that are, well, incredibly powerful for building complex molecules with pinpoint precision.
Yeah, and our mission today is to truly unpack these fascinating cycloadditions for you. We'll explore the mechanistic reasoning behind them, their unique pathways, the critical role of stereochemistry, how functional groups transform, and even how to think retrosynthetically about their construction.
Right. We want to give you a clear conceptual understanding that goes beyond just memorizing facts.
Exactly. And we'll connect it all back to your existing knowledge of molecular structure, conjugation, and the reactivity of familiar functional groups like alkenes and heterocycles.
So let's jump right in.
Okay, so when you think about most organic reactions, you're probably picturing what we call ionic mechanisms. Electrons move from an electron-rich site to an electron-poor one.
Right. The usual suspects.
Yeah, often creating fleeting, unstable intermediates like carbocations or carbanions. Imagine forming a cyclic ester, a lactone, that can easily involve like 5 steps and 4 different cationic intermediates. It's a series of discrete electron movements.
But pericyclic reactions,
Yeah.
they completely break that mold. Instead of electrons flowing in a single direction, they move in a closed loop, often visualized as a perfect circle. And here's the game changer. There are no intermediates at all.
None. These reactions happen in one beautiful concerted step. It's a fundamental difference.
And the quintessential example, the one that truly changed our understanding, is the Diels-Alder reaction. It proceeds with surprising ease, often just by, heating the starting materials.
It's truly remarkable how the electrons reorganize. 2 pi bonds essentially vanish, and 2 new sigma bonds form simultaneously. It's like a molecular handshake, incredibly efficient and direct.
And the reason it works so incredibly well lies in its transition state. This fleeting arrangement of atoms has 6 delocalized pi electrons, giving it this special aromatic character, much like benzene.
That inherent stability of the transition state is the secret sauce, really. It makes the Diels-Alder such a powerful low-energy pathway for building rings. It was truly a paradigm shift in how we understand molecular interactions.
A huge shift.
Indeed. This groundbreaking reaction was discovered by Otto Diels and Kurt Alder back in 1928, and it earned them the Nobel Prize in 1950. Its utility extends from fundamental research to big industrial applications like the synthesis of the agricultural fungicide, Captain. It's a real workhorse of organic synthesis.
Okay, so let's break down the components of this incredible reaction. You need 2 main players, right? A duana and a dienophile.
Exactly. The dinane, first, must be conjugated, meaning alternating single and double bonds. But there's a crucial catch. It has to be able to adopt and cease conformation.
Cease, meaning the double bonds are on the same side of the single bond connecting them.
Precisely. The divas here refers to that sigma bond, but Diana, for instance, typically prefers the more stable is transformed thermodynamically, but it can rapidly rotate into that necessary cis conformation to react. It's usually not a major barrier.
And then you have stars like cyclopentadiene, which is a fantastic diene because its cyclic structure permanently locks it in that cis conformation, makes it incredibly reactive.
Exceptionally reactive. Conversely, dienes that can't get into an cis conformation, like maybe some cyclic dienes where the double bonds are forced into an is-trans arrangement, they simply won't participate in a Diels-Alder reaction. The ends just can't get close enough to react.
Makes sense. Okay, what about the other partner, the dienophile?
Now, for the dienophile, this is usually an alkene. The key characteristic here is often an electron withdrawing group conjugated to the alkene. Think of things like carbonyl compounds, nitro groups, nitriles, even sulfones attached right next to the double bond. These groups activate the dienophile, making it more receptive, more electrophilic.
So simple alkenes, like ethylene, they're generally not very good dienophiles on their own.
Not really, no. They can react under harsh conditions, but it's slow. In fact, if you try to combine a highly reactive diene, like our friend cyclopentadiene, with a weak dienophile, you'll often see the cyclopentadiene reacting with itself.
Oh, right. One molecule acts as the diene and another as the dienophile.
Exactly. It dimerizes. Shows you just how reactive cyclopentadiene is and how much activation helps the dienophile. Historically, this reactivity was used to make pesticides like dieldrin and aldrin, though they were later banned due to environmental issues.
Okay, so thinking retrosynthetically, identifying a Diels Alder product.
Yeah.
What are the key features you look for?
It's quite satisfying, actually. Look for a new six-membered ring. That's the hallmark. Then look for a double bond inside that new ring. And often you'll find that electron withdrawing group that was part of the original dienophile now sitting outside the ring, usually on the opposite side from the new double bond. Spot those features, and it's a strong candidate.
And reversing it is even easier, you said.
Oh, yeah. It's one of the most straightforward retrosynthetic disconnections. You literally just draw 3 curved arrows going in reverse around the cyclohexene ring, breaking those 2 sigma bonds and reforming the pi bonds of the diene and dienophile. It's incredibly powerful for simplifying the synthesis of complex 6-membered ring structures.
And the conditions are usually pretty simple.
Typically, yeah. You often just heat the components together, maybe 100 to 150 degrees Celsius. Solvents and catalysts often aren't even necessary, although sometimes you might use a sealed tube if your reagents are volatile to keep them contained.
Okay, now here's where the elegance truly shines for me. The incredible control over stereochemistry. You mentioned this earlier.
Absolutely. The Diels-Alder reaction is completely stereospecific. This is huge. Any stereochemistry present in your starting dienophile is directly, faithfully translated into the product.
So if you start with a cis dienophile, you get a cis relationship in the product.
Exactly. The classic illustration uses dimethyl malate, which is a cis dienophile, versus dimethyl fumarate, which is trans. Malate gives a product where the ester groups remain cis to each other in the new ring, and fumarate gives a product where they are trans. It's almost as if the diene approaches and adds on top of the dienophile, locking in that precise 3D arrangement. No scrambling.
That level of control must be invaluable in areas like drug discovery, where specific 3D shapes are critical.
Incredibly valuable. And it's not just the dienophile. The diene's geometry also dictates the stereochemistry. If the diene is substituents, their relative positions are maintained in the product too. Because the reaction is concerted, everything happens at once, and molecular symmetry is conserved.
Okay, that makes sense. But now, you mentioned something earlier that sounded odd, the endo rule.
Ah, yes, the endo rule. It initially seems counterintuitive. In many irreversible Diels-Alder reactions, you often see a kinetic preference for the less stable endo product over the more stable exo product.
Wait, hang on. The less stable product forms faster. Why would that happen?
It's a great question. It seems backwards, right? The reason lies in a subtle but crucial secondary orbital interaction in the transition state leading to the endo product.
Secondary orbital interaction.
Okay. Imagine the diene approaching the dienophile. In the endo approach, there's a favorable, though non-bond-forming overlap between the electron-deficient groups of the dienophile, like carbonyls, and the developing pi bond system at the back carbons of the diene, the ones not directly forming the new sigma bonds.
So an extra bit of attraction even though it's not forming a bond there?
Precisely. This extra interaction, this secondary overlap, lowers the energy of the transition state for the endo pathway compared to the exo pathway, making the endo route faster, even if the final endo product itself is slightly more sterically hindered and less stable thermodynamically.
Wow, okay. That's subtle but powerful.
It really is. And all these observations, why the Diels-Alder works in the first place, why specific activating groups are needed, the stereospecificity, this endo preference, they all find their elegant explanation in frontier molecular orbital theory, or FMO theory.
Right, FMO theory. This helps explain why the electrons move the way they do.
Exactly.
Yeah.
It's one of the great triumphs of modern theoretical chemistry. Instead of just drawing arrows, it looks at the interacting orbitals. In simple terms, for a cycloaddition like this to happen thermally, you need the highest occupied molecular orbital, He-SOMO, of one molecule, and the lowest unoccupied molecular orbital, LUMO, of the other molecule, to have the correct symmetry for effective overlap as they approach each other.
Correct. Symmetry. Meaning they can constructively interfere to form bonds.
Yes. If the symmetries don't match, like if you try to combine 2 simple alkenes thermally in a 2+2 fashion, the orbital lobes don't align properly for bonding at both ends simultaneously. You get bonding at one end, antibonding at the other, no reaction.
But with a dienophile.
With a diene and an activated dienophile, the symmetry is perfectly aligned between the diene's HOMO, which looks a certain way, and the dienophile's LUMO, which is lowered in energy by that withdrawing group. This allows productive bonding interactions to occur simultaneously at both ends, forming those two new sigma bonds in one go.
And this also explains why electron-deficient dienophiles and electron-rich dienes are the best partners.
Exactly. The electron withdrawing group on the dienophile lowers its LUMO energy. An electron donating group on the diene would raise its HOMO energy. This brings the HOMO of the diene and the LUMO of the dienophile closer in energy. A smaller energy gap means better interaction, better overlap, a lower energy transition state, and a faster reaction.
Okay, that ties a lot together. Now, you mentioned something else surprising, reactions in water.
Ah, yes, the on-water effect. It's fascinating. For a reaction that involves mostly nonpolar hydrocarbons, you wouldn't expect water to be a good solvent. But it turns out these non-ionic Diels-Alder reactions can often accelerate dramatically in water, sometimes by hundreds, even up to 700 times.
Oh.
Well, the thinking is that water acts as an anti-solvent. The organic molecules don't dissolve well, so they're forced together into tight clumps or micelles. This hydrophobic effect effectively increases their local concentration and might also organize the transition state favorably, promoting the reaction and sometimes even enhancing that endoselectivity we talked about. It's a really interesting aspect, especially for green chemistry.
Very cool. Okay, so we've covered stereochemistry. What about regioselectivity? What happens when both the diene and dienophile are unsymmetrical? How do you know which end connects to which?
Another great question. Just like in other reactions like Michael additions, where a nucleophile prefers to attack one end of an activated alkene, there's a preference here too. It comes back to those frontier orbitals.
Yeah.
Unsymmetrical dienes and dienophiles have distorted HOMOs and LUMOs, meaning the electron density, or more accurately, the orbital coefficients, are larger at certain atoms.
So the bond formation happens faster between the atoms with the biggest orbital coefficients.
That's the idea. On formation is considered to be more advanced in the transition state between the atom with the largest coefficient in the diene's HOMO and the atom with the largest coefficient in the dienophile's OLUOMO. That dictates the major regioisomer.
Is there a simpler way to predict it, maybe without drawing all the orbitals?
There's a helpful trick, actually. You can imagine a hypothetical ionic stepwise mechanism. Now remember, the reaction is concerted, not ionic. But if you think about which end of the diene would be more stable as a partial positive charge, like an allelic occasion, and which end of the dienophile would be more stable as a partial negative charge, like an enolate, it often correctly predicts how they'll line up.
Ah, like a mental shortcut.
Exactly. And it leads to a useful mnemonic for the common cases. If you have an electron-donating group on the diene and an electron-withdrawing group on the dienophile, the major product usually has an ortho or para relationship between these groups in the final cyclohexene ring. Think of it like this. The Diels-Alder reaction has an aromatic transition state that is ortho and para-directing.
Okay, that's a handy rule of thumb. Can you influence this regioselectivity?
Absolutely. Lewis acids can be game changers here. They act as catalysts.
How do they catalyze it?
The Lewis acid coordinates to the electron withdrawing group on the dienophile, usually a carbonyl oxygen or maybe a nitrile nitrogen. This coordination makes that group even more electron withdrawing.
So it pulls even more electron density away.
Right. This lowers the dienophile's LUMO energy even further, making the reaction faster. It also tends to exaggerate the difference in the size of the LUMO coefficients at the two ends of the alkene.
Making the preference for one connection even stronger.
Precisely. So Lewis acid catalysis not only speeds up the Diels-Alder, often allowing it to proceed at much lower temperatures, maybe even room temperature, but it also dramatically enhances the regioselectivity. You can go from a modest preference to almost exclusively one regioisomer. Tin tetrachloride, SnCl4, is a common example.
Got it. So the Diels-Alder is clearly a superstar, but it's just one type of cycloaddition, right? Chapter 34 covers others too.
Definitely. It's part of a larger family of paracyclic reactions. While Diels-Alder is the most famous 4+2 cycloaddition, 4 pi electrons from the diene, 2 from the dienophile, there are others. For instance, 1003 dipolar cycloadditions.
Okay, 1003 dipolar sounds different. What's the dipole?
A 1003 dipole is essentially a 3-atom system that has 4 pi electrons spread over those 3 atoms with charge separation. Think of things like ozone, azides, or a really common one in synthesis, nitrones.
Nitrone.
Nitrones are great examples. They have this N-oxide structure. They act as the 3-atom, 4-electron component. They react with a dipolariphile, which is usually an alkene or alkene, similar to a dienophile. This is a 3+2 cycle addition forming a 5-membered ring.
So 4 plus 2 gives 6-membered rings. 3 plus 2 gives 5-membered rings.
You got it. And what's cool about nitrones is that the initial 5-membered heterocyclic ring product, an isoxazolidine, contains a relatively weak NO bond. You can selectively cleave that bond, often by reduction, like with zinc or catalytic hydrogenation.
And what does that give you?
It gives you a 1,4,3 amino alcohol. And because the cycle addition is stereospecific, you get this amino alcohol with defined stereochemistry based on the starting materials. It's a fantastic way to build that important 1,4 and 3 relationship between an alcohol and an amorin.
That sounds incredibly useful synthetically.
Oh, it is. There are other 143 dipoles too, like nitrile oxides, which have a CN triple bond component. They also do 3+2 cycle additions with alkenes or alkynes. And again, you can manipulate the resulting 5-membered ring, an isoxazoline or isoxazole, to get other useful functional groups like 1,4,3 hydroxyketones or amino alcohols, again with stereo control. The synthesis of the vitamin biotin uses a really elegant intramolecular 1,4,3 dipolar cycle addition to set key stereocenters.
Wow. Okay, so 5-membered rings via 3 plus 2. What about other ring sizes or related reactions?
Well, there are also 2+2 cyclid additions, 2 components, each contributing to pi electrons. Now, thermally, trying to just stick 2 simple alkenes together to make a cyclobutane ring is generally disallowed by orbital symmetry rules. The FMOs don't match up correctly, like we discussed.
Right, the symmetry is wrong for a thermal reaction.
But you can make it happen photochemically. If you excite one of the alkenes with UV light, you promote an electron to a higher energy orbital, changing the orbital symmetry requirements. Now, the excited state alkene can react with a ground state alkene in a 2+2 fashion.
So light provides the energy and changes the rules, basically.
Pretty much. Photochemical 2+2 reactions are useful for making 4-membered rings. They are also stereospecific, but they don't usually follow an endo rule. Sterics tend to dominate.
Are there any thermal 2 plus 2 reactions that work?
There are some important exceptions. These happen with specific types of activated alkenes, namely ketenes, which have a CCO unit, and isocyanates, NCO. These molecules have a unique orbital geometry, kind of twisted, that allows them to undergo thermal 2+2 cycle additions with regularly alkenes or imines.
Ketenes. Those react to form 4-membered rings, too.
Yes, ketene plus an alkene gives a cyclobutanone. Ketenes are very reactive. Dichloroketene, for instance, reacts readily with cyclopentadiene in a 2+2 manner, even faster than the Diels alder. Then you can remove the chlorines later. This is key for making got-lactams, the core structure of penicillin antibiotics, often by reacting a ketene with an imine.
Okay, fascinating. So we have 4 plus 2, 3 plus 2, 2 plus 2. Any other key players?
2 more really important reactions that involve cycloaddition mechanisms, even if we don't always think of them that way, are specific oxidations. First, osmium tetroxide, OSO4 dihydroxylation.
Making diols from alkenes.
Exactly. OSO4 reacts with an alkene in what can be viewed as a 3+2 cycle addition to form a cyclic osmate ester. The crucial point is that this addition happens to one face of the alkene. When you hydrolyze that ester, or use a catalytic cycle with NMO, you get a syn-diol. Both hydroxyl groups are added to the same face. That syn stereochemistry is a direct consequence of the concerted cycloaddition mechanism.
So the mechanism dictates the stereochemical outcome.
Very neat. And the second one is ozonolysis, O3. This is the classic way to cleave a double bond right in half.
Right, ozone chews up double bonds. How does that work? Is it a cycloaddition?
It's actually a remarkable sequence of cycloadditions and reverse cycloadditions. Ozone itself is a 1,4,3 dipole. First, it adds to the alkene in a 3+2 cycloaddition to form a highly unstable primary ozonide or malozonide.
Okay, step 1, cycloaddition.
Step 2. This malozonide immediately falls apart via a reverse 3+2 cycle addition, breaking into an aldehyde or ketone and a carbonyl oxide, which is another reactive 1003 dipole.
Whoa, it breaks apart and makes another dipole.
Exactly. And then step 3, that carbonyl oxide immediately undergoes a third cycle addition, another 3+2, with the aldehyde or ketone that was just formed to make the more stable secondary ozonide.
A cycloaddition, a reverse cycloaddition, and another cycloaddition. That's quite a cascade.
It really is. And then you treat that final ozonide with different reagents depending on what you want. A reductive workup, say with dimethyl sulfide or zinc, gives you aldehydes or ketones. An oxidative workup, maybe with hydrogen peroxide, gives carboxylic acids. Or you can even reduce it further with sodium borohydride to get alcohols. It's incredibly versatile for breaking CT bonds cleanly.
So wrapping this all up then, cycloadditions, whether it's the Diels-Alder, the 1,3-D polar types, or these oxidative processes, they're just incredibly elegant and powerful tools.
Absolutely. They offer single-step or carefully orchestrated multi-step pathways to construct rings and complex molecular architectures, often with fantastic control over stereochemistry and, as we saw, regioselectivity.
And the underlying principle, the reason they work so well and so predictably, really comes down to orbital symmetry.
That's the key unifying concept. The seemingly magical efficiency and specificity aren't magic. They're governed by the fundamental rules of how electron orbitals interact. It's a beautiful testament to the predictive power of theoretical chemistry in understanding and designing reactions.
Looking ahead, there are still more paracyclic reactions to cover, like electrocyclic reactions and sigmatropic rearrangements, which I believe are in Chapter 35.
That's right, the paracyclic story continues.
So a final thought for you, our listener.
Oh.
Consider how understanding this subtle dance of electrons, the symmetries of these invisible orbitals, allows chemists to design reactions that build molecules with the kind of intricacy and precision we see in nature itself. It influences everything from new medicines to advanced materials. What other seemingly impossible transformations might a deep understanding of orbital symmetry unlock in the future?
A great question to ponder.
Thank you for joining us on this deep dive into the fascinating world of cycloadditions. We hope you've enjoyed being part of the Last Minute Lecture family.